Well, this is Chapter 21. It's our review. It's Part 3 review for the inferences about variables. So we're going to go back over data production, some of the data basics. We call our subjects either individuals or subjects. The variable, there can be categorical versus quantitative. We look at units of measurement, explanatory versus response variables. The data production basis, observational versus experimental. Remember, observational studies and experiment study. Observational studies, we can only make associations. We'll experiment because we can hold certain things fixed. We can say this causes that. When we do this production, when we want to get our data, we have to make sure we do simple random samples, or we have completely randomized experiments. Now from these, going back up to the variables, categorical, remember, are just things that are characteristics of a person or a thing, whereas quantitative is a measurement. So again, if my variable was color of shirt, red, blue, green, or yellow, and the other one, that's categorical. Quantitative would be the height of a student, their weight, things like that. And the units of measurement, again, I didn't want to gloss over that, but you have to know what things are being measured in. It's very important. That's why we tell you to put them on your Graphs and Minitab if we have units of measurements to put that on there. Now you have to beware of really bad data production. It can make interpretation almost impossible or very unreliable. Voluntary response and confounding can be quite difficult. Now, weaknesses in data production can make generalization very, very difficult. So generalizing to the population, just unreliable. So if we got responses, we say all college students think this, but our sample only came from one campus, not a good thing. Now, once we have the data, we went into data analysis. We plotted our data. We looked for overall patterns and then striking deviations like outliers from the overall pattern. We add numerical descriptions based on what you see. Now, one quantitative variable, we did graphs, stem plots, histograms, box plots, and probability plots. The pattern we looked at, the distribution of the shape, the center spread, did it have outliers? And then we talked about the density curve to describe the overall pattern. And we dealt a lot with normal curves and the student t-distributions. The numerical descriptions, the 5-number summary, or, which is measurements where we're talking about positional measurements, and X bar and S, the mean and the standard deviation, which are more center of gravity and that spread. Now, the things you have to be careful about. Averages and other simple descriptions can miss the real story. We have to be careful of lurking variables and the effects of outliers. It can be deadly, and the effects of influential observations. Now, however, if we have good data, we have a good data collection, we have good summaries, inferences use that sample data to infer conclusions about the population, and they'll be good if our samples are good. Data should come from simple random samples or randomized comparative experiments so that we can use the law of probabilities to help us make these inferences and to give them a quantitative value. Always examine your data before doing inference. Inference often requires a regular pattern such as roughly normal with no strong outliers. And a key idea to always keep in your head is what would happen if we did this over and over and over again. That's the key to statistics and inferential statistics. It's all about repeatability. Then we got into doing confidence intervals. You estimate a population parameter, but that only, if you just do a statistic, that's only a point estimate. With confidence intervals, we can now make an interval about a particular parameter. The method captures the parameter approximately stated percentage of the time. So a 95% confidence interval, if we constructed that confidence interval over and over again, 95% of those intervals would capture the true mean. Now, the margin of error of the confidence interval does not include the effects of practical errors. That is, things like when you're getting the data under coverage and non-response. Margin of error deals with the probability. Then we have significance tests. assessing evidence against the null hypothesis in favor of an alternative hypothesis. So a p-value, the probability of a typo and error based on your sample, the smaller that p-value, the stronger the evidence against the null hypothesis. Now, if H0 were true, how often would I get an outcome favoring the alternative this strongly? Statistical significance at a particular level, 0.05 for example, so if our p-value is less than a particular significance level, means that an outcome this extreme would occur less than 5% of the time if H0 were true. Now, 0.05 is not sacred. We said that that was one of the more common, sort of baseline or a number that we look at, but it can be 0.01 or 0.001 or any number really. It's just a probability. So statistical significance is not, so don't get hooked just that it's always, the p-value is less than 0.05. It's up to the discretion of whoever does the test. Statistical significance is not the same as practical significance. So in other words, if something comes out, you do the test of significance, and it ends up being statistically significant, it might not be practically significant. So, oh yeah, they have a difference, but it's by 0.1, their heights. Yeah, there's a statistical difference, but practically speaking, they're only 1 micron apart, so it wouldn't make a big difference. So practically speaking, it doesn't make a big difference. So there is a difference between those two. Large samples can make small effects significant, and small samples can fail to declare large effects of significance. Now, when we do our methods of inference, we have to choose the right inferential procedure, carry out the details, and state your conclusion. So when you're doing it, you have to make sure all assumptions are met and that you're doing the right test for the right problem. So there's this wonderful diagram that's in your book, sort of a tree diagram. You start out with your problem, test a claim, or estimate a parameter. That's 2 ways you can go. That's that first arrow going out. And estimating a parameter, that's our confidence intervals. We had the 1 sample and the 2 sample. With the 1 sample, we did means and proportions. For the 2 sample, we did the difference of means and the difference of proportions. So this is a great grid or diagram to look at to help to know which particular test you should use.